All right, so I kind of want to wrap up a few things in this segment here. First of all, I want to talk about dispersion. And dispersion is this phenomena that where we see white light is actually composed of the whole rainbow. And here is this famous picture from Pink Floyd's Dark Side of the Moon record, and here we see white light coming in and being bent into the rainbow by this prism. And the basic idea here is not too hard to understand. Red light just gets bent less than does violet light. And to see why that is, we need to really zoom in on the index of refraction. Remember, the index of refraction tells us, well, first of all, it tells us how fast light travels in a given medium. Remember, a higher index of refraction means a slower speed of light in that particular medium. And up until now, we've just assumed that the index of refraction was defined by a medium and was the same for all wavelengths, for all colors of light. And broadly speaking, that's mostly kind of true. If we really zoom in, though, and we really inspect this, we find that it is not completely true. Notice that we're talking about the second decimal place here, right? And we see a slight variation with wavelength. So we see that red light has a slightly lower N value than does purple light. And these are just two different types of glass. But we'd find that basically all glass and plastic does have some of this effect. And we call this dispersion. So when different frequencies travel at different speeds, that phenomenon is called dispersion. We've used this equation quite a bit in waves. And we've said that the velocity is determined by the type of wave and the medium it's moving through. And it's independent of wavelength and frequency. And that is still a fantastic model for almost all situations. But there are a handful of phenomena that just get lost by that model. And we have to zoom in a little bit more. And we see a really careful analysis shows that velocity does have a slight dependence on frequency, which gives us this spreading out of light into a rainbow, which is, again, called dispersion. And so we see that if we had two identical prisms here, we could send white light in, it would get dispersed into its rainbow, and we could collect it back together into white light. However, if we were to exclude all the colors but one, let's say we use a little slit here to select the green ray, then we'll find that the green ray bends, but we don't get white light back out. So again, a prism does not change the color. The prism can spread the colors out. So we think of white light then as being a collection of a whole bunch of different frequencies, a whole bunch of different wavelengths, which, when put together, our eyeballs perceive as clear or white light. And this gives rise to one of my favorite things, a rainbow. So you'll only see a rainbow when the sun is at your back, and it turns out that it is refraction from inside tiny water droplets that causes a rainbow. And so we've seen lots of pictures in cartoons and such of raindrops that look like that, and that it's a very artistic, lovely raindrop. It turns out it's not true. It turns out that the surface tension of water is so much greater than any sort of aerodynamic forces that might be coming along here, that for small droplets, they are almost perfect spheres, even if they're falling. So this is a real raindrop. That's a cartoon raindrop. So real raindrops are almost perfectly round, and the sun comes in one side. As it passes through, it gets bent a little bit. Then it reflects off the back side. This is total internal reflection. So that's pretty cool. And then it bounces out and into our eyeball, which means that the red light is coming from a different droplet than the blue light is coming from. Also pretty cool. Into your eyeball, right? Now someone over here is getting red light and green light from different droplets. So that's pretty cool. And it turns out that that angle is from 42.5 to 40.8 degrees. And so you'll only see a rainbow under these conditions, when the sun is behind you, and you will see this ring at that angle, between 40 and about 42 degrees from the angle of the sun's rays. So that's pretty cool. Some of you might remember this video. It's about 10 years old. The double rainbow. It's so exciting. I don't know how well you can see this here, but what we should be able to see is that the colors get reversed here, don't they? This is a very nice double rainbow. Here we see red kind of on the outside, and in the double rainbow, we see red on the inside. I also think the double rainbow is really cool. Check out what goes on in a double rainbow. The reason why we get that flip is because in a double rainbow, there's an additional bounce. So for a double rainbow, light comes in here, and then out. So in a double rainbow, there's an additional reflection. There's two reflections in a double rainbow, which causes the colors to flip. So in a single rainbow, we see the red on the outside, but on that second ring, we see red on the inside. I'm not sure it is geometrically possible to get a third bounce for the triple rainbow. So in the last couple chapters, we've sort of fudged a number of things. It turns out that spherical lenses don't actually form a perfect focus. They're pretty darn close, but they don't form a perfect focus. It turns out that the rays from the outside of the lens focus at a slightly closer point than the rays from the inside of the lens. So you need a more sophisticated shape. Turns out you need a parabolic shape, and with a parabolic shape, you can achieve one perfect focus. This actually happened to the folks who designed the Hubble Space Telescope. So the Hubble is a telescope based on mirrors forming images and not lenses, but that's okay. It works very similarly. And spherical mirrors have this problem as well. And you'd think they would have gotten this right on the first time, but they actually just didn't, right? So this was what the images from the Hubble looked like initially. They did not properly correct for the spherical aberration in their mirror. And they actually had to, they weren't sure if they were going to be able to make it work, but they were able to design some corrective optics. They gave the Hubble telescope glasses, is what they did. And they were able to correct for this spherical aberration. So we're not going to go into this in a ton of detail, but part of what I wanted to do in this segment is just sort of mention some caveats. That in a lot of what we've been talking about, things are a bit more complicated than what we've gone into so far. It turns out that if we get a rainbow because different colors bend different amounts, that means we're not going to get a clear focus either from different colors. So different colors will focus at different points. Why? Because they have slightly different n values. So we can correct that with a high power low dispersion lens combined with a low power high dispersion lens. And this takes some doing to figure this out, but we can make it so that all of the colors meet. So these last couple slides about these aberrations, this is part of why it takes many years of optometry school to learn how to build good glasses that work for everybody. It's also why if you look at your glasses, they might say +2, but they're not just shaped like that, right? It's just a bit more complicated. The last topic I wanted to mention in this segment is we talked about diffraction a couple of chapters ago. And it turns out that the diffraction of waves is just such an interesting thing. So here we see when wave fronts pass through a single opening like this, we get diffraction effects. We get these fringes, much like what we talked about last chapter. We get this pattern of fringes, a central bright spot, and then a pattern of alternating light and dark. We don't just see a shadow of that circular opening because it's small compared to the wavelength of light. And it turns out that if the diffraction pattern from one object overlaps the diffraction pattern from another object, it becomes impossible to resolve or to see those two objects. So here is an example of an image made with a telescope. So this is two stars actually, but you can't even tell that they are two stars. Why? Because their diffraction patterns are overlapping. And so we say that these are not resolvable. Here we can just barely tell that there are two stars, and here we actually see an image of both stars. And so we can do a little bit of mathematics, and we can say, okay, as long as the bright spot of image 2 falls on the first dark fringe of image 1, then we ought to be able to resolve those stars. And it just turns out that their angular separation has to be equal to at least this in order for us to resolve them and tell that there are actually two stars and not just one. So this limits our ability to use light to view objects. It limits our ability to magnify objects using just ordinary light. Here is a picture of some E. coli, and here we see the picture with an optical microscope. So this would be using the physics we've discussed in this chapter. And notice that these are quite fuzzy. And this little thing here, these little bars, this indicates the approximate wavelength of light that was used to create this image. And you can see that these are fairly well resolved, but you know, like these guys that are next to each other, they're starting to fuzz into each other. And how about this? How many E. coli do we see here? You really can't tell, right? So these are not resolved. We don't know how many of them there are here. However, notice that this dependence upon the wavelength, right? So if we had a much smaller wavelength, then we could have a much smaller angle between two objects and still resolve them. And so here we've created this image with an electron microscope. And so this is using electrons as waves. We're going to find out in a couple of chapters that when we're talking about very microscopic, the tiniest of the tiny, that things behave as much like particles as they do like waves, like electrons. We've thought about them probably as a little ball winging around a nucleus. And it's not really that great of a model. It's better to think about it as a standing matter wave around the nucleus. And we can use this idea in all kinds of applications. So we can actually use the wave-like nature of electrons to form an image. That's what is happening here. And the wave-like nature of electrons, it allows us to have a much, much smaller wavelength. A smaller wavelength gives us better resolution. So ultimately, that's what's happening here. We have no trouble seeing these different individual bacteria in this image, but we do in this image. Why? Because here we're using something with a much, much smaller wavelength. And so that's a little bit of a hint into some of the really cool stuff we're going to talk about next when we move into some modern physics.